Hello everyone. I'm welcoming you all to this session to discuss about the topic arithmetic for computers in the first unit. So as we already discussed, CPU is going to be the important unit in computer, and in central processing unit this arithmetic and logic unit is going to be the key component which is responsible for performing all the addition and subtraction, multiplication and division operation. And in this session we will discuss about how this addition and subtraction is going to be carried out. If you just see the block diagram, maybe, so this is going to be the block diagram that represents the arithmetic and logic unit. Okay, here if you just see, as the name implies, this unit is responsible to perform all the arithmetic operations like addition, subtraction, multiplication, division, and the logical operations. What we mean by logical operations, it can be XOR operation, OR operation, not operation, like that. All logical operations can also be performed. So to perform these operations, this unit needs some inputs. So the input for this unit will be provided by the operand registers. So the registers will get the data from the memory and it will feed the arithmetic and logic unit. And what is the operation to be done and when it is to be done, all these things have to be controlled by means of the control signals. So having received the control signals and the input operands from the registers, this ALU will perform the desired operation, and the final outcome of this operation will be just given through the result registers, and also it will be reflected in the flags. So this is going to be the basic functionality of an arithmetic and logic unit. Now we will just see how actually this unit is going to perform this addition and subtraction operation. Now coming to this addition, before seeing this addition operation, we have to be very clear with how the data is going to be represented. Of course, we have discussed this data representation in detail in the second topic. Okay, now as a quick recap of how data is going to be represented, we will just see there are three types of representation. So one is called as signed magnitude representation. The next one is called as ones complement representation. And then we have two's complement representation. Totally we have three types of representation of the numbers. So one's complement, two's complement representation. Okay, so now we will discuss how the number is going to be represented in all these categories. Maybe for just for example, we can just take a number 10. Okay, so if nothing is there, then we will take it as a positive number, and we will be in a need to represent minus 10 also. So we will just have two representations. So first we will see one by one. So coming to the signed magnitude representation, how it will be represented. So first you take the binary equivalent of 10. So the binary equivalent of 10 is 1010. Okay. So hope you all know how to convert this number, decimal number, into binary. So probably you'll be doing this Dana division. Okay, 5 2s are 10, the remainder is 0. 2 2s are 4, the remainder is 1. Okay, and then 1 2 is 2, remainder is 0. So again you just divide till the quotient becomes 0. So this is going to be the number you are going to get. So you collect all the remainders in this direction. So it is 1010. So the binary equivalent of this is 1010. Another method is you can just follow this 8421 code. Okay. Here I want 10, so I will put 1 in 8th place and then in this unit place. So how this number is achieved is, here it is going to be 2 power 0, 2 power 1, and this is 2 power 2, and this is 2 power 3. So like this we can represent the number in the binary weightage. So 2 power 3, it is 8. So the weight, any number present in this particular position will have the value 8. So now I want to represent 10. So 8 plus 2, 10. Okay, and the remaining bits will be 0. So the binary representation of plus 10 is 1010. And usually we deal with an 8-bit number. So if you are going to take an 8-bit representation of this number, now we have to convert this 4-digit number into an 8-bit number. So that means we need to add 4 more bits. And whenever you represent a number, this is signed magnitude representation. So you have to represent the sign also. So the sign will be always represented in the MSB bit position. The first bit is always, MSB bit is always reserved for sign bit, and if it is a positive number you will be always representing it 0. 0 represents positive, and all the remaining unused bits, it will be extended with the sign bit content. So whatever is a sign bit, that will be extended. So here I will be padding with this 0, Because the sign bit is 0, I will just insert 0 here, I will insert 0 here. So this is going to be the sign bit representation of plus 10. Hope it is clear to you. Now we will just see what is the sign bit representation for minus 10. Again for minus 10, first write the magnitude. So magnitude of this 10 is nothing but 1010, and then we have to represent in 8 bits, so 4 more bits to be added. And as we all know, this is going to be the MSB is going to be the sign bit. Because it's a negative number, you will always write it as a 1. So the one important point you have to remember, plus is represented with 0 and minus is represented with 1. So this is a negative number, so I represent this bit as 1. And then the remaining bits, what we have to do, so the remaining bits, it has to be extended with a sign bit. And in the normal sign magnitude representation, we will represent this bit as 1, and then we will be just filling it up with zeros. So this is going to be the sign bit representation of minus 10. Plus 10 and minus 10 in sign magnitude representation we have written. Now we will just see what is the ones complement representation. So in the ones complement representation, for positive numbers, we will write the numbers as such. There is no difference for positive numbers. So in ones complement also, we will be having the same number 0, 0, 0, 1, 0, 1, 0. And for ones complement representation for minus 10, whatever is the value for plus 10 you have written, now take ones complement of this number. So what will be the ones complement of this number? It is 1, 0, 1, 0, and then you will be having all ones. So you just flip the number 0 to 1 and 1 to 0. This forms the negative minus 10. So ones complement representation of minus 10, you take ones complement of the positive equivalent. Okay. Now coming to 2's complement representation, how you will represent the number in 2's complement? Again for positive numbers there is no difference. So the same number will be repeated as such without any change. For positive number it is not going to differ. But when coming to negative minus 10 in 2's complement representation, what you have to do? You have to add 1 to the 1's complement value. Then you will be getting the 2's complement value. 1 plus 1 it is 1 0 0 1 1 0 1 1 1 1. So the 4 plus 4. So this is going to be the 2's complement representation of minus 1. Now to summarize, given a number plus 10 or minus 10, how to represent in all these three representation? The first representation is sign magnitude. You find the binary equivalent of this number, then the sign bit you have to decide by looking at the sign. If it is positive number, put a 0. If it is a negative number, put a 1. Then you just fill up all the remaining bits with zeros. This is going to be for sign magnitude. Coming to one's complement representation and two's complement representation, it is going to be one and the same for positive numbers. So all the positive numbers will have the same binary pattern in all the three representation. So this one's complement or two's complement comes into picture only for negative numbers. So in the negative numbers, how you will take for minus 10, you write the plus representation, positive value, and then take one's complement of this number. It will give you the one's complement representation. And for two's complement representation, write the positive value like this, and for this you take two's complement. And taking two's complement, there are two steps, two methods available. You first take one's complement, then you add 1 to the LSB, that will give you two's complement. Another straightforward method is, if a number is given like this, if they ask you to find the two's complement representation in single step, then what you have to do, you scan the number from the right hand side, so you copy all the numbers till you encounter the first one. So this is 0, so you copy the number as such. Okay, the first one you copy the number as such. Okay, and once you have copied, once you have encountered the first one, thereafter all the remaining bits will be flipped. It has to be inverted. So if it is 0, you will be taking it as 1. If it is 1, you will be taking it as 0, and all zeros you will be taking it as 1. So this is going to be the 2's complement representation of the given number. So there are two methods. You take 1's complement of this number, add 1, that will give you the 2's complement value. Otherwise, straightforward method, you take this number, scan the number, copy the number bit by bit as such till you encounter the first one. So till you encounter the first one, you copy the bits as such. And once the first one is obtained, thereon the remaining bits have to be flipped. So if it is 0, you have to write it as 1. If it is 1, it is going to be 0. This is going to be the straightforward method for representing the 2's complement value. I think this will be clear to you. And another important point what I would like to emphasize is this weighted method. So in the weighted method, how we will represent negative numbers. So there is another important format here. So now we have 8, 4, 2, 1. So if I want to represent number in 8 bits, so what you have to do? So this is 2 power 0, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, then 4th bit, 5th bit, 6th bit, 7th bit, and 8th bit. Okay, so 0 to actually 0 to 8, 8 bits means you are not going to include this. Now here it's 2 power 3 is 8, 2 power 4 is 16, 2 power 5 is 32, and then 2 power 6 is 64, and then 2 power 7 is 128. So in the weighted method, so this is going to be the weight which you are going to allocate for each bit position. So like this you are going to allocate. If it is a positive number, you will just write the 1 in each of this location. For negative numbers or for 2's complement representation, how you will represent minus 10? Okay, let us represent plus 10 here. So how you will represent plus 10? So I want the value 10. So this is 8. So in this position I will write a 1. Okay, and then if I add 2 I will get 10. So 8 plus 2 10. So I will just write 1 and 1 here, it is plus 10. So all the remaining bit positions I will be writing it as 0. So 0 0 0 0. So this is how I will be getting in the weighted method. And now if I want to find minus 10, so for negative numbers, how the values are going to be considered. So this MSB bit, whatever is the weighted value assigned in the MSB bit, that will take the negative value. Okay, so minus 128, it's a negative number. I have to get a negative number. So I will be putting a 1 here. So because it is a negative number. Then what should I do? What should I subtract from minus 128 so that I will be getting plus 10. So with minus 128, if I subtract or if I add 138, sorry, 118, if I add 118, I will be getting a 10 here. So 8 minus 8 is 0, 2 minus 1 is 1. So, okay, I want to get 10, magnitude 10. So, I should be in a position to find minus 118. Okay, minus 128, if I add 118, I will be getting 10. So, minus 128. Then to get 118, what should I do? I will put a 1 here. Okay, then I will put another one here, another one here. Okay, so what it comes to, so I have to take 64, then 32, then 16. Okay, then what should I do? I will be putting a 0 here in the 8th bit position, then another one here. Okay, another one here, 0. So now if I just find the equivalent, how I will be finding the equivalent? This minus 1 is represented as minus 128, so I will be writing minus 128, and this one represents 64, then the next one represents 32, then 16. Okay, then 4, then 2. So now if we add all the positive numbers, 6 plus 4 10, 12, 13, 14, 18. So 8, 1, 6 plus 1 7, 10, 11. So I will be getting 118. So from minus 128, if I add plus 128, I will be getting minus 10. So this is what I will be finding the equivalent. So to find the equivalent negative numbers, so you will write the notation like this. Hope it's clear to everyone. Maybe if it is not still clear, maybe we will find one more number so that it will be still more clear. Suppose for example, if I want to represent plus 16, okay, if we want to represent plus 16 and minus 16, how we will write the binary equivalent? So 16, here itself I have 16, so I will put a 1 here, and then I will put 0 in all the remaining bits. So this will be equivalent to plus 16. So this is the plus 16 equivalent. Now coming to minus 16, always this negative number should be kept 1. Okay, so I will put a 1 here, and then what number should be added with minus 128 so that I will be getting plus 16. So how should I do? Let me write first, then I will just do the calculation. Okay, so the plus 16 is this one. Okay, 0 0 0 0 1 1 1. Okay, now I will just check the value whether I will be able to get the minus 16 value. So this one represents minus 128. Okay, then here I have 64, then I have 32. Okay, then I have 16. So 6 plus 4 10, 10 plus 2 12, 2 1. Okay, 6 plus 4 10 11. So 112. So 128 minus 112, it is going to be 6. Okay, then here it is going to be 16. So I have got 16. So the binary equivalent of this is minus 16. Now I think it's clear to everyone. So for plus 16, If I take weighted values, I will just put a 1 here and all the remaining bits 0. If it is minus 16, this MSB should be 1, only then I will get a negative number. And to this minus 128, if I add all this equivalent weightage, then I will be getting minus 16. So this completes the discussion of binary